Okay, welcome to Unit D, Equilibrium. So the premise of this unit is that up until now we've assumed that all reactions, two things react together and form a product, and that's 100% yield. In terms of then all the reactants are gone and they've all become products. And this is for sure the case in terms of things like combustion reactions. You know, if I'm burning wood, the wood definitely disappears and all becomes products. Soot and carbon dioxide and carbon monoxide. So a combustion reaction definitely deserves that 100% arrow. And everything we've been doing so far, like stoichiometry, is 100% arrow going forward. But that's not actually how all reactions take place. In some reactions, what you have is, let's do like a formation reaction where I have two elements coming together and making a product. But at the same time, remember, there's not just two, there's like 6 billion trillion and 6 billion trillion. So two of those out of the 6 billion trillion come together and form a product. And then some of the products decompose to replace back my elements. And so what you end up having in your flask is a mixture of the elements becoming compounds and the compounds decomposing into the elements. And the reaction's going both ways. So that's what equilibrium means. It means that I don't get 100% completion, but rather I get both kinds of reactions happening. So here are some all right. So the rate of the forward, this is the definition. The rate of the forward reaction equals the rate of the reverse reaction. So that means that how fast my formation is happening is how fast my decomposition is happening. So 1 per second, 1 per second, or 5 per second, 5 per second, right? The rate of the forward equals the rate of the reverse reaction. It has to be in a closed system. So that means like the lid has to be on. It has to be a constant temperature because as soon as you change the temperature, you can change the shift. We'll talk about that when we talk about Le Chatelier. And a mixture, you end up with a mixture of reactants and products overall. So that's super important to remember when you're talking about things like color, right? If this was pink and this was blue, I would end up with some kind of purple-ish color in my flask because I have the presence of everything there. Okay, so here are some normal examples for you where you already have an equilibrium existing in your everyday life. So let's talk about a closed bottle of pop. So in your bottle of pop, what you have is you have gas on the top and you have the liquid at the bottom, right? And so in this closed, I'm going to try to draw this. In this closed bottle of pop, good enough, right? I have my gas particles becoming my liquid particles, like dissolving into the liquid. But for every one that dissolves, I release a particle of gas. And what you have is you have the same amount of pressure in the top of that bottle. If I squeeze that bottle today, it's the same pressure as if I squeeze it tomorrow. The only thing that would change that amount of pressure that you feel in the bottle would be if I change the temperature, right? Like on a hot day, you can see it kind of expanding, right? So you get it? That's right. And it expands on hot days. Just had to rethink that. Okay, so what about a closed bottle of perfume? Same idea. I have my liquid perfume and I have my gas perfume. And unless I spray it, right? Like let's change this into a perfume bottle now with a little trigger here. Unless I spray it and release some of those, so that would not be closed system anymore, but an open system. So as soon as I don't spray any, then that's still a closed system where I have a dynamic equilibrium between the gaseous molecules and the liquid molecules. Again, a diffused air freshener in a car. So we're gonna those little trees, and we're gonna take that tree. Okay, I'm gonna take that tree and I'm gonna open up the package and it's gonna stink. And all these particles are going to come off of this air freshener, and it's going to be super concentrated around the air freshener and pretty dilute over at the far end of the car. But eventually these start diffusing, right? And so in my whole car, I'm going to end up with the same amount of air particles around that car. Now, this particle doesn't stay there, but rather it will move, right? Gas travels in a straight line until it hits, the outside of the container, or another particle. And so that will go this direction. But for every one that moves this way, one has to move that way, because the smell remains the same throughout the whole car, right? The diffusion is diffused. And so until you get the concentration gradient that's the same. And so once that concentration gradient is maintained, or is established, then it's maintained by, for every one that goes in that direction, one has to come back in that direction. And so once you've diffused something, those particles don't just freeze in time, but rather they continue traveling. But for every 5, I get 5, right? The rate of the forward equals the rate of the reverse. And in that case, like the forward of the car and the reverse of the car, actually, so like literally. Okay, so blah, blah, blah. Got it? Awesome. So there's an example in your notebooks that say like, find which of the following is is dynamic equilibrium established. And so one of these would be the answer. It has to be closed. It has to be constant temperature. And you have to see something like this. So one of them is a closed bottle of pop. So that'll be the right answer for that one. Then there's a saturated solution. So we're about to talk about that one in a second. And I was going to say something else, but I forgot. Okay. Oh yes, but if it was like an open ice melting in the water situation, then the water can evaporate, right? And so like just evaporation in normal everyday life. And so unless I had my ice melting in my water with a lid on, then it's not going to be equilibrium. Okay, awesome. Right, so let's talk about a saturated solution, because that's the one that you're going to see a lot of. And this is actually something that we covered in Chem 20 already, where we talked about dynamic equilibrium, like always moving. And so I have this saturated solution here that's a typical example. So I'm going to take some table salt, some sodium chloride, and I'm going to dissolve it in some water, and it's going to dissociate into its ions. No problem. So here's a picture. Here's my lump of salt at the bottom of my cup, and my dissolved ions, and water is present too. So I've just put that species up there, but I don't want to talk about it right now. So it's just there. Okay, so this pile will stay at 3 grams, for example. I just picked a number. So if that is 3 grams, it will stay 3 grams forever, right? As long as there's no evaporation of this water, as long as I put a lid on this cup, then tomorrow and the next day and the next day and the next day, it'll be 3 grams. But you can actually radioactively tag the nuclei and follow its pathway. So if I were to make that nucleus just slightly heavier, you can't see that, slightly heavier than the other nuclei, then I can actually watch it. And what happens is that doesn't stay in the solid. It actually becomes an ion, Na+. And when that happens, you have to have the Cl- form as well. But that mass is still 3 grams. So for every one that dissolves, I must have another compound that recrystallizes and goes back into the NaCl. So because if I'm dissolving some and it stays at 3 grams, I better bring some in for it to maintain the 3 grams. Okay, so this is a Chem 20 example of dynamic equilibrium in a saturated solution where as much dissolving as I have recrystallizing. And so how we write that, not in a paragraph, but rather just in an equation, is this. Here I have my solid, and it is dissolving into these 2 ions. So obviously going in this direction is called dissolving, or a dissociation reaction, right? Remember those from Chem 20? And then in this this is a funny arrow, right? This arrow is saying, hey, I'm talking about the forward direction. And this arrow is saying, hey, I'm reading it backwards. And these 2 ions are coming together to form that solid again. And that's called recrystal, crystallizing. Right? So I've got recrystallization happening and dissolving happening, and the rate of the forward for every 5 that dissolve per second equals the rate of the reverse. 5 per second must recrystallize at the same time in order to maintain that 3 grams and it not fluctuate like 3 grams, 8 grams, 7 grams, whatever, right? So in order for it to maintain the 3 grams, it has to, the rate of the forward has to equal the rate of the reverse. So that's what these funny arrows mean. It means I can go forward and backwards. And you've seen these funny arrows in your redox table, right? Where we say, hey, I can go that way or I can go that way. And so, right, my battery's running low, even though I have it charged. Crap. I'll fix it later. Okay, so what else did I want to say to you about this? Oh yes, sometimes we don't write our arrows perfectly equal, but rather sometimes we make them different lengths. And that's to show you in terms of like, if I have, like in this pile, because I know that I can dissolve a lot of sodium chloride, right? It's very soluble, that I will have a lot more ions than I would have solid. And so because of the dissolving is really easy, then I would end up with this arrow being super big sometimes and that arrow being smaller. Sometimes they're equal, sometimes they're bigger. It's just like what are you trying to communicate? There's no like right answer unless it asks you to indicate with arrows. So here's one. So I have nitrogen from the air, hydrogen, which is a byproduct from the oil industry, and we put them together and we make ammonia. Now that ammonia is really important in Alberta because it goes and it makes fertilizer. So you see this reaction a lot. This is called a Haber process. And so you see it a lot in this unit because the byproducts are super important, right? Fertilizer in Alberta, especially right now in the spring, like this is a big deal. So this reaction exists in equilibrium. Now that's kind of like whatever, right? Like that's unfortunate because if I'm trying to sell this stuff, I want every bit of nitrogen and hydrogen to come together and make it, but it doesn't because as soon as I make it, some of it decomposes. It's really annoying. We'll talk about how the industry helps shift that to make more product and make more money in next week. Okay, so, oh yes. So, and actually, not only does some of it decompose, but actually more of it decomposes. I have in my flask, if I were to draw a picture of this, I would have to draw way more nitrogens and hydrogens than ammonia. So here's just one ammonia. And then nitrogen, hydrogen, 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 nitrogen, hydrogen, hydrogen, hydrogen. It's getting messy now. But you can see that my ratio is not stoichiometric. It's not 2 to 3 to 2, but rather I have way more of my reactants than I have of my products. So that's what this arrow is saying. It's saying that. Let's take vinegar, right? If I have vinegar solution, a tiny bit of it ionizes, right? It's such a weak acid that only 1% of it ionizes into my acid and my CH3COO minus ethanoate ion. And so because a tiny bit, 1%, sometimes we even put these percentages over the arrows. So only 1% of it dissociates, a tiny bit dissociates, and most of it stays into that molecular compound, not the ions. Okay, so that is the introduction to equilibrium, outcome A and B. And have a go at writing these. Make sure you memorize that definition, super important, and memorize those conditions.